Hey everyone! Ever wonder what the world of tomorrow will be made of? Imagine materials that are stronger, lighter, or even self-healing. How about metals that remember their shape or fabrics that clean themselves? The future of materials is pretty incredible, and today, we're diving into 7 of the most fascinating innovations that might just change everything. Join us as we explore these breakthroughs and prepare to be amazed by what science has in store. Graphene, the wonder material. Alright, let's talk about graphene. You might have heard it called a wonder material, and honestly, it's not an exaggeration. Imagine this. Graphene is a sheet of carbon atoms arranged in a honeycomb pattern, just one atom thick. But here's where it gets wild. It's around 200 times stronger than steel, conducts electricity better than copper, and is so light you can barely feel it. Pretty amazing, right? Graphene is popping up in a ton of different fields, and it's basically revolutionizing technology. Picture this. Flexible phone screens that you can fold without breaking, or batteries that charge faster and hold way more power. That's the kind of potential we're talking about. Some researchers even say graphene could lead to phones that charge in seconds instead of hours. And think about electric cars that can drive hundreds of miles longer on a single charge. This isn't just hype, it's real potential that's being explored in labs around the world. Now, graphene is also being looked at for water purification. Imagine being able to filter seawater into drinkable water quickly and easily, using something as simple as a graphene filter. This could be huge for areas where clean water is a luxury. With the right development, graphene could truly change lives in the most fundamental way by providing easy access to clean water for millions. And we're not just talking tech. Think medical breakthroughs, biocompatible implants that last longer, stronger yet flexible materials for prosthetics, and sensors that could detect diseases earlier. Graphene's strength and conductivity mean it could support a new wave of medical advancements, potentially transforming healthcare as we know it. So, that's graphene for you. A material with more applications than we can count and a future that's looking brighter every day. It's light, strong, flexible, and honestly, it's just getting started. The impact it could have on everything from our gadgets to our health is mind-blowing. Transparent aluminum, stronger than glass. Alright, get ready because transparent aluminum is straight out of science fiction. Imagine something that looks just like glass but is way stronger, more resilient, and can even withstand bullets. That's transparent aluminum, also known as aluminum oxynitride or ALON. It's a material made from aluminum, oxygen, and nitrogen, and it's actually clear like glass. But here's the kicker, it's nearly as strong as steel. So how does it work? Well, ALON is created by processing it under extreme heat and pressure to give it a crystalline structure that's not only tough but also super resistant to scratches and impacts. Think of it like the armor of the future, only see-through. Right now, it's being tested for military applications like bulletproof windows, protective shields, and even cockpit canopies for jets. Imagine having a window that's as clear as glass but can take on serious hits without cracking. That's the magic of transparent aluminum. Now think about what this could mean for our everyday lives. Imagine having phone screens made from transparent aluminum. Drop your phone? No problem. With ALON, you'd have a screen that's practically indestructible. This material could also replace glass in car windows, giving us vehicles with windows that are both lightweight and incredibly safe. And even in architecture, transparent aluminum could allow for skyscrapers with windows that can withstand extreme weather, all while being lighter than traditional materials. And it's not just about toughness. ALON is resistant to both extreme temperatures and chemical corrosion, which makes it perfect for space exploration. Picture this. Future spacecraft with transparent shields that can survive the harsh conditions of outer space while giving astronauts a clear view of the cosmos. Transparent aluminum is still expensive to produce, so we won't see it everywhere just yet. But it's getting closer, and as the tech advances, it could become a game changer for so many industries. This glass of the future could transform everything from smartphones to skyscrapers, giving us strength, durability, and clarity all in one amazing material. Self-healing concrete. Say goodbye to cracks. Ever noticed how cracks just seem to pop up everywhere, on sidewalks, bridges, and even buildings? It's one of those things we've just accepted, right? Well, self-healing concrete is here to change that completely. Imagine concrete that, instead of crumbling over time, actually repairs itself. Sounds like sci-fi, but it's real, and it's one of the most exciting innovations in construction today. So how does it work? Self-healing concrete has tiny capsules inside it filled with special bacteria or healing agents. When a crack forms, moisture gets in and activates these capsules. Then boom, the bacteria come alive and start producing limestone, filling the crack and sealing it up, all without any human help. It's like the concrete is alive, patching itself up every time it takes a little damage. No more endless maintenance and patchwork. This concrete is built to last. Now think of the impact this could have. Bridges that don't need constant repairs, buildings that can handle years of wear and tear, and even roads that can withstand harsh weather, all without us having to spend millions on repairs every few years. Not only does this save money, but it also reduces waste and makes our infrastructure more eco-friendly. And in a world where cities are growing faster than ever, having materials that can practically take care of themselves is a massive game changer. Some places are already testing this amazing material, adding it to structures to see how it holds up in the real world. Sure, it's still a bit pricier than regular concrete right now, but with time and more research, self-healing concrete could soon become the go-to for construction everywhere. Imagine walking down a sidewalk or driving over a bridge knowing the material beneath you can heal itself, staying strong and safe for years to come. Self-healing concrete is paving the way for a future where cracks are no longer a constant problem, and our cities can stand tall for generations without falling apart. Metal foam, light as a feather, strong as steel. Picture this, a material that's as strong as metal but light enough to practically float. Sounds wild, right? Welcome to the world of metal foam. This stuff is engineered to be ultra-light, packing serious strength with just a fraction of the weight. Imagine the potential here, not just in construction but in everything from vehicles to protective gear. It's a true superhero among materials, combining durability with incredible lightness. So, what exactly is metal foam? Think of a sponge made of metal. It's filled with tiny pockets of air which make it super lightweight but still tough as nails. The real magic is in how these air pockets absorb energy. If you put metal foam in a car, for example, it could help absorb the impact during a crash, making vehicles safer without adding tons of weight. Less weight means better fuel efficiency, so it's not only protecting passengers, but also reducing fuel consumption. Talk about a win-win. Metal foam has some pretty impressive heat resistance too. It can handle extreme temperatures, which opens doors for all kinds of applications. Imagine skyscrapers built with a material that can withstand intense fires or armor that can absorb shock without being heavy. It's like having the strength of steel with none of the bulk, making it ideal for next-gen technology and cutting-edge designs. And let's not forget its environmental benefits. Since it uses less material than solid metal, we're talking about a lower carbon footprint in production. Plus, it's recyclable. So we're not only creating something strong and light, but also something sustainable. In short, metal foam is changing the game. It's a material that's tough enough to protect, light enough to innovate, and smart enough to use in countless ways. With metal foam, the future is looking lighter, stronger, and just a little bit cooler. Aerogel, the frozen smoke. Ever heard of a material that's so light it's practically weightless? Meet aerogel, also known as frozen smoke. This stuff is like something out of a sci-fi movie. It's incredibly light, almost transparent, and has an insane ability to insulate against heat. When you see it, it almost looks like a ghostly mist, but it's actually solid and can be strong enough to support objects hundreds of times its weight. Crazy, right? So what makes aerogel so special? It's made by removing the liquid from a gel and replacing it with gas, leaving behind a solid network that's 99% air. That's why it's so light and why it feels like you're holding a piece of cloud. Despite its delicate appearance, aerogel can handle extreme temperatures, which makes it perfect for insulation. In fact, it's been used in spacesuits and on Mars rovers to protect against the intense cold of outer space. Aerogel isn't just for outer space, though. Picture it used in buildings to create insulation so effective it could cut down on energy bills big time. Think windows that keep out the heat in summer and hold in warmth during winter, all thanks to a material that barely weighs anything. It's the kind of tech that could make homes and offices way more energy efficient, helping the planet and your wallet. And there's more. Aerogel can be made from a variety of materials like silica, carbon, and even polymers, giving it different properties for all sorts of applications. Carbon aerogel, for example, can be used in batteries to improve performance without adding weight. With this adaptability, aerogel is paving the way for lightweight, efficient solutions in everything from electronics to environmental cleanup. Aerogel really is one of those materials that defies logic. It's feather light, yet insulating, delicate-looking, yet incredibly durable. The potential here is massive, whether we're talking about cleaner energy, better electronics, or advanced building materials. It's frozen smoke, but make no mistake, this is solid science at its finest. Carbon nanotubes, strength in small packages. Imagine a material so tiny you can't see it with the naked eye but strong enough to support loads beyond what most metals can handle. That's the magic of carbon nanotubes. These little structures, just a few nanometers thick, are revolutionizing how we think about strength and flexibility in materials. Despite their size, they're one of the toughest things out there. 50 times stronger than steel, but so light they almost don't seem real. Here's how they work. Carbon nanotubes are essentially rolled-up sheets of graphene, which, if you remember, is already a wonder material. By rolling it into a tube, scientists have created a structure that's not only incredibly strong but also has remarkable electrical conductivity. It's a bit like wrapping a sheet of paper into a straw. It suddenly gains more strength along its length. But these nanotubes, they're on a whole other level, capable of handling serious stress without snapping. The potential uses of carbon nanotubes are jaw-dropping. Think about super strong, lightweight materials for aircraft, cars, and even sports equipment that are far tougher but don't weigh nearly as much. Engineers are already exploring nanotubes for building cables and structural supports that could transform construction as we know it. Imagine buildings that are stronger and can withstand more while using fewer materials. And it doesn't stop at strength. Carbon nanotubes also conduct electricity like champs. This makes them game changers in the tech world, with applications in next-gen batteries and high-efficiency electronics. Scientists are even working on using nanotubes to create flexible screens and wearable tech. Imagine a phone or tablet screen that you can bend without breaking. Carbon nanotubes are making that vision possible. So we've got these tiny, super strong, and incredibly versatile structures that could change everything from transportation to electronics. Carbon nanotubes may be small, but their impact is massive. They're setting the stage for a future where materials are lighter, stronger, and more efficient. Proof that sometimes big things really do come in small packages. Liquid metal, the shapeshifter. Alright, get ready for one of the coolest materials out there, liquid metal, the ultimate shapeshifter. Imagine a metal that's not just super strong, but also incredibly elastic, like a metal that thinks it's rubber. Liquid metal, also known as amorphous metal, takes on this almost alien property because, at an atomic level, it's arranged in a random pattern, rather than the neat crystalline structure you find in regular metals. This gives it a set of qualities that make it behave unlike any other material out there. So what makes liquid metal so amazing? For starters, it's ridiculously tough. We're talking stronger than titanium, but able to bounce back to its original form when it's bent. Imagine bending something as tough as steel and having it snap right back without a scratch. That's the power of liquid metal. And because of its unusual structure, it's also scratch-resistant, so it can handle the rough and tumble of everyday life without wearing down. This material has already made its way into products we use every day. Apple's used it in iPhones, it's in high-end watches, and it's even in medical devices and sports equipment. Its super smooth finish and resistance to wear mean that anything made from liquid metal feels as premium as it gets. Plus, because it can be cast in molds with incredible precision, manufacturers can create detailed, intricate shapes with a perfect finish. No need for all that extra machining. And the applications for liquid metal go way beyond what we're seeing today. Think of it in car parts, aerospace engineering, and even robotics, where having materials that are both strong and flexible can be a game changer. Engineers are excited about its potential in everything from surgical instruments to spacecraft components because liquid metal can take a beating, hold its form, and keep performing. Imagine the next generation of technology is not only stronger but also far more durable thanks to this shape-shifting metal. So, there you have it, liquid metal, the material that's rewriting the rulebook on what metals can do. It's tough, it's flexible, and it's ready to reshape industries in ways we're only beginning to imagine. In a world where durability and precision matter more than ever, liquid metal is showing us that the future of materials is more exciting and sci-fi than we ever thought possible. And that's a wrap on the 7 materials that could redefine the future. From self-healing concrete to lightweight metal foam, these materials are pushing the boundaries of what we thought was possible. If you enjoyed this journey into the world of groundbreaking materials, don't forget to like, share, and subscribe to InnoVision Tech. Hit that bell icon to stay updated with our latest videos. Until next time, keep exploring the wonders of innovation with us. Ever wondered what mysteries lie beyond the blue horizon of Neptune? From its supersonic winds to its hidden ocean of liquid water, this distant giant planet is full of astonishing surprises. Neptune, the eighth planet from the Sun, remains one of the most enigmatic members of our solar system. What makes it so unique, and why does it capture our imagination? Join us for an incredible journey into the heart of Neptune's wonders, where science meets the extraordinary in a world of blue. Neptune is a windy wonderland. Neptune is a planet of extremes, and its winds are no exception. This gas giant holds the title for the fastest winds in the solar system, with speeds reaching up to 1,200 miles per hour. That's nearly 5 times faster than the strongest hurricanes on Earth. These incredible winds create a dynamic and chaotic atmosphere, with giant storms and dark spots moving across the planet's surface. The planet's winds are fueled by Neptune's internal heat, which radiates more energy than it receives from the Sun. This heat drives massive convection currents, creating powerful jet streams and vortices that rage across the atmosphere. These winds give Neptune its ever-changing weather patterns, despite its frigid distance from the Sun. One of the most famous weather features on Neptune was the Great Dark Spot, a storm system the size of Earth. Discovered by the Voyager 2 spacecraft in 1989, this giant storm vanished just a few years later, showcasing the dynamic nature of Neptune's atmosphere. Scientists are still studying what makes Neptune's winds so extreme. The planet's unique combination of internal heat, atmospheric composition, and rapid rotation all play a role, but the exact mechanisms remain a mystery. The winds of Neptune are a testament to the raw power of planetary weather, offering a glimpse into a world where nature reigns supreme. The deep blue mystery of Neptune's color. Neptune's striking blue color is one of its most defining features, but it's not just a simple reflection of the sky. This rich azure hue comes from methane in the planet's atmosphere, which absorbs red light from the sun and reflects blue light back into space. However, methane alone doesn't fully explain Neptune's intense coloration. Scientists believe that there are other, unknown components in the atmosphere that enhance the blue tone. These mystery molecules have yet to be identified, making Neptune's appearance as much a scientific puzzle as it is a visual marvel. Neptune's vivid blue sets it apart from its neighbor Uranus, which also contains methane but appears a paler shade of blue-green. The subtle differences in atmospheric composition between these two planets highlight just how unique Neptune truly is. The planet's color isn't just an aesthetic feature, it provides valuable clues about the composition and chemistry of its atmosphere. By studying Neptune's blue, scientists gain insights into the processes at work on this distant world, and even on exoplanets that share similar characteristics. Neptune's mesmerizing blue reminds us of the beauty and complexity of our solar system, where even the color of a planet holds untold secrets. The discovery of Neptune was a mathematical marvel. Neptune's discovery in 1846 wasn't a stroke of luck, it was a triumph of mathematics and astronomy. Scientists noticed that the orbit of Uranus wasn't following predictions, suggesting the gravitational pull of an unseen planet. Using calculations, French mathematician Urbain Le Verrier pinpointed Neptune's position without ever looking through a telescope. When German astronomer Johann Galle aimed his telescope at the predicted spot, Neptune was there, just as Le Verrier had calculated. This marked the first time a planet was discovered through mathematical prediction rather than direct observation, a breakthrough that changed the course of astronomy. Interestingly, English mathematician John Couch Adams had also made similar calculations around the same time, leading to a controversy over who deserved credit for Neptune's discovery. In the end, both Le Verrier and Adams are recognized for their contributions. Neptune's discovery also underscored the power of Newton's laws of motion and universal gravitation, which formed the basis of the calculations. This event cemented the idea that mathematical models could predict the existence of celestial objects, a concept that continues to guide modern astronomy. The discovery of Neptune stands as a testament to human ingenuity, showing how the mind can uncover worlds hidden from the eye. Neptune's rings are thin and wispy. Neptune is adorned with a set of faint, thin rings that add to its otherworldly charm. These rings, made of dust and ice particles, are far more delicate and less prominent than those of Saturn. There are 5 main rings: Gale, Leverrier, Lassell, Arago, and Adams, each named after notable scientists who contributed to our understanding of the planet. What makes Neptune's rings unique is their clumpy and uneven distribution, a phenomenon scientists are still trying to understand. Some parts of the rings appear brighter and denser, forming arcs rather than smooth, continuous bands. These arcs are thought to be stabilized by the gravitational pull of Neptune's moons, particularly Galatea. The rings were first detected in the mid-1980s through ground-based observations and were later confirmed by the Voyager 2 spacecraft. Voyager's flyby provided detailed images of the rings, revealing their complex structure and composition. Despite their faintness, Neptune's rings hold valuable information about the planet's history and the processes that shaped its outer regions. By studying the rings, scientists hope to uncover clues about the formation of the outer solar system and the interactions between moons and planetary rings. Neptune's rings may not be as famous as Saturn's, but they are a delicate reminder of the intricate beauty found throughout the cosmos. Neptune is an ice giant with a hidden ocean. Neptune belongs to a category of planets known as ice giants, which are distinct from gas giants like Jupiter and Saturn. Beneath its thick atmosphere lies a mantle of water, ammonia, and methane ice, creating an interior vastly different from the gas giants. This icy composition gives Neptune its classification, but it also raises intriguing possibilities. Scientists believe that under the icy mantle lies a vast ocean of superheated, high-pressure water. This ocean, kept in a liquid state by extreme pressure, could potentially harbor exotic forms of life or unusual chemical processes. Neptune's core is a rocky mix of silicates and metals, surrounded by this mysterious ocean. The transition from the icy mantle to the core is gradual, creating a layered structure that adds to the planet's complexity. The pressure and temperature in Neptune's interior are so extreme that methane molecules could break apart, forming diamonds. These diamonds might sink to the core, creating a glittering layer of solid carbon, a phenomenon often referred to as the diamond rain. Neptune's status as an ice giant with a hidden ocean sets it apart as a planet full of surprises, challenging our understanding of what a world can be. Neptune's moons are a diverse family. Neptune is home to 14 known moons, each with its own unique characteristics. The largest and most famous is Triton, a fascinating moon with a retrograde orbit, meaning it orbits Neptune in the opposite direction of the planet's rotation. This unusual motion suggests that Triton was likely captured from the Kuiper Belt, a region of icy objects beyond Neptune. Triton is a world of wonders, featuring geysers that spew nitrogen gas, a thin atmosphere, and a surface covered in frozen nitrogen and methane. Its geologically active surface makes it one of the most intriguing moons in the solar system, and a prime candidate for future exploration. In contrast to Triton's icy splendor, Neptune's smaller moons are less dynamic but no less interesting. Proteus, the second largest moon, is oddly shaped and heavily cratered, suggesting it has remained relatively unchanged for billions of years. Nereid, another notable moon, has one of the most eccentric orbits of any moon, swinging dramatically closer and farther from Neptune. These moons offer a glimpse into the diverse processes that shape planetary systems. Some moons are likely remnants of Neptune's original satellite system, while others, like Triton, are later additions. Studying them helps scientists understand how moons form and evolve over time. Neptune's moons are a microcosm of the solar system's complexity, each contributing to the rich tapestry of this distant planet. Neptune's magnetic field is misaligned and tilted. Neptune's magnetic field is unlike any other in the solar system. It's both off-center and tilted at a staggering 47 degrees relative to the planet's rotational axis. This means that Neptune's magnetic field is constantly shifting, creating a wildly dynamic magnetosphere. The magnetic field is generated by electric currents within the planet's icy mantle, rather than in a metallic core as on Earth. This difference in origin contributes to its unusual properties, including its irregular shape and strength. In some regions, Neptune's magnetic field is up to 10 times stronger than in others. This chaotic magnetic field produces spectacular auroras, much like the northern and southern lights on Earth. However, Neptune's auroras are more scattered and less structured, appearing as patches of glowing light near the poles. The planet's unique magnetosphere also interacts with the solar wind in ways that are still not fully understood. Voyager 2 provided the first glimpses of Neptune's magnetic behavior, but many questions remain about how it affects the planet and its surrounding space environment. Neptune's magnetic field adds another layer of intrigue to this distant world, highlighting the diverse ways planets generate and sustain magnetic forces. Neptune's year lasts 165 Earth years. A year on Neptune is an extraordinary 165 Earth years long, meaning it takes nearly 2 centuries to complete one orbit around the Sun. Since its discovery in 1846, Neptune has completed just one full orbit, which occurred in 2011. This lengthy year is due to Neptune's vast distance from the Sun, about 30 times farther than Earth. At this distance, the Sun appears much smaller in Neptune's sky, providing only a fraction of the light and warmth that reaches our planet. Despite its slow orbit, Neptune rotates rapidly on its axis, completing a day in just 16 hours. This rapid spin, combined with its elliptical orbit, creates fascinating seasonal variations. Each of Neptune's 4 seasons lasts more than 40 Earth years, resulting in gradual but significant changes in atmospheric activity. Understanding Neptune's lengthy year and slow seasonal shifts provides valuable insights into the dynamics of planetary orbits and climate systems. The planet's orbit also places it in a region of the solar system that offers clues about the formation of outer planets and the migration of celestial bodies. Neptune's epic year serves as a reminder of the vast scales of time and distance that define the outer reaches of the solar system. Neptune was the last stop for Voyager 2. In 1989, NASA's Voyager 2 spacecraft became the first, and so far only probe, to visit Neptune. This historic flyby provided humanity's closest look at the distant planet, revealing breathtaking details about its atmosphere, moons, and rings. Voyager 2 captured stunning images of Neptune's vibrant blue clouds, powerful storms, and faint rings, transforming our understanding of the planet. It also made groundbreaking discoveries, such as the presence of the Great Dark Spot, the dynamic weather patterns, and Triton's geysers. The spacecraft's instruments measured Neptune's magnetic field, confirming its tilted and off-center configuration. Voyager 2 also provided data on the planet's temperature, wind speeds, and atmospheric composition, laying the foundation for future studies of ice giants. Voyager 2's flyby lasted only a few hours, but its legacy endures. The mission's data continues to inform scientific research and inspire new questions about Neptune and its role in the solar system. The encounter with Neptune marked the end of Voyager 2's planetary tour, but the spacecraft remains a symbol of humanity's quest for knowledge, now traveling through interstellar space as a messenger of discovery. Neptune may hold clues to the formation of exoplanets. Neptune's status as an ice giant makes it a valuable analog for studying exoplanets, planets beyond our solar system. Many of the exoplanets discovered so far are Neptune-like in size and composition, falling into a category known as mini-Neptunes or sub-Neptunes. By studying Neptune, scientists can better understand the atmospheric processes, magnetic fields, and interior structures of these distant worlds. Neptune's dynamic weather, deep blue hue, and icy mantle offer a template for modeling the conditions on similar exoplanets. One of the most intriguing aspects of Neptune-like exoplanets is their potential habitability. While Neptune itself is inhospitable, its characteristics help researchers identify which exoplanets might have liquid water, stable atmospheres, or conditions suitable for life. Future missions to study Neptune up close, such as orbiters or atmospheric probes, could provide critical data for interpreting observations of exoplanets. These missions would also deepen our understanding of how planets like Neptune form and evolve in different stellar systems. Neptune's connection to exoplanet research highlights its importance not just as a member of our solar system, but as a key to unlocking the mysteries of the universe. Neptune is a planet of mysteries, extremes, and beauty, offering a glimpse into the farthest reaches of our solar system. From its supersonic winds to its hidden ocean, Neptune continues to captivate scientists and dreamers alike. If you enjoyed this exploration, be sure to like, share, and subscribe to InnoVision Tech. Don't forget to hit the bell icon to stay updated with our latest videos. Until next time, keep exploring the wonders of the universe with us.
What if time isn't a straight line but something more flexible? Something that under the right conditions could fold, twist, or even repeat? Scientists have explored this idea through Einstein's relativity, quantum mechanics, and theories of closed time-like curves. Some believe time loops are purely fiction. Others think they could be hidden in the very fabric of reality. So let's dive deep into the theories, paradoxes, and real-world experiments that just might prove that time loops aren't just Hollywood magic, they could be real. Time loops. Imagine waking up to the same morning over and over again, every action you take, every word you speak, every choice you make resetting like a broken record. Sounds like science fiction, right? But what if I told you some of the brightest minds in physics have seriously considered the possibility that time itself might not always flow in a straight line? Instead, it could loop, bend, or even fold back on itself, trapping events in an endless cycle. We've all seen movies and shows where characters get stuck in a time loop, repeating the same day, trying to break free, or using their knowledge of past loops to their advantage. But is this just a Hollywood fantasy, or could the fabric of time actually allow for such strange phenomena? Could time loops be real? Could you, in some bizarre twist of physics, find yourself reliving the same moment indefinitely? The idea of time loops isn't just some wild storytelling device. It has roots in deep scientific theories, some of which suggest that under the right conditions, time might not be as linear as we assume. From Einstein's relativity equations to the mind-bending possibilities of quantum mechanics, certain interpretations suggest that time loops might not be entirely impossible. In fact, some theories imply they could already be happening, hidden from our everyday experience. But before we dive into the theories and research, let's break down what a time loop actually is. Is it a glitch in the universe, a natural occurrence, or just a human illusion? Let's find out. Gödel's rotating universe. What if I told you that, mathematically speaking, time travel might already be possible, at least on paper? In 1949, the legendary mathematician Kurt Gödel proposed something that could rewrite everything we think we know about time. He wasn't just any mathematician, this was the same genius behind Gödel's incompleteness theorems, which shook the foundations of mathematics itself. And when he turned his attention to Einstein's general theory of relativity, what he found was nothing short of mind-blowing. Gödel discovered a solution to Einstein's equations that described a rotating universe, a cosmic dance where space and time weren't just linear, but could actually loop back on themselves. In this model, time wasn't a one-way street, it was a circular highway where, theoretically, you could travel along a certain path and end up in your own past. Yes, that means time loops could be a built-in feature of our universe, if Gödel's model were correct. So how does it work? Imagine the entire universe spinning like a giant whirlpool. As space twists, time gets caught in the motion, forming what physicists call closed time-like curves, CTCs, pathways where an object or person could move through space-time and arrive at an earlier point. This essentially creates a time loop, a scenario where past and future aren't strictly separated. But before you start making plans to visit ancient civilizations, there's a catch. Gödel's universe requires a very specific type of global rotation, one that doesn't match our observations of the real universe. Modern cosmology tells us that while the universe is expanding, there's no clear evidence that it's rotating in the way Gödel's equations describe. So does this mean time loops are impossible? Not necessarily. Gödel's work showed that time itself might be more flexible than we assume, opening the door for other theories that could one day prove that loops in time are more than just science fiction. Closed time-like curves. What if time wasn't a straight path but a loop? What if you could take a walk through space-time and, instead of moving forward into the future, you ended up back in your own past? Sounds crazy, right? But according to some interpretations of Einstein's theory of general relativity, this might not just be possible, it could be a fundamental feature of the universe. Enter closed time-like curves, a theoretical concept that allows time itself to twist and reconnect, forming loops that could trap events in an endless cycle. Imagine drawing a timeline on a piece of paper. Now, instead of keeping it straight, you bend it into a circle so the starting point eventually connects back to itself. That's a CTC, a space-time path where an object, or even a person, could travel and end up exactly where they started, but at an earlier point in time. This isn't just a thought experiment. solutions to Einstein's field equations actually allow for CTCs under specific conditions. One of the most famous examples is Gödel's rotating universe, which showed that if the universe had a certain type of spin, time loops could naturally form. Other proposals, like wormholes and rotating black holes, also suggest that if space-time were bent the right way, closed time-like curves might emerge. But here's the big question. If CTCs exist, why don't we see time travelers popping up at random? That's where things get tricky. Some physicists argue that nature might have built-in safeguards to prevent time loops from forming freely. Stephen Hawking's chronology protection conjecture suggests that quantum effects could destroy any time loop before it fully forms, ensuring that paradoxes never occur. Still, the fact that CTCs are mathematically possible raises a profound question. If the universe can allow time loops, does that mean they exist somewhere out there? Or are we just scratching the surface of something far bigger than we can comprehend? Novikov's self-consistency principle. Alright, let's say time travel is possible. You step into a time machine, travel back a few decades, and decide to change history. Maybe you want to stop a major event from happening, or classic time travel trope, you prevent your grandparents from meeting. Boom! You've just created a paradox, a contradiction that could break the very fabric of reality. But what if I told you that some physicists believe time itself wouldn't allow such paradoxes to exist? Enter the Novikov self-consistency principle, the ultimate rule book of time travel. Proposed by Russian physicist Igor Novikov in the 1980s, this principle suggests that if time loops exist, the universe has a built-in mechanism to prevent paradoxes. In other words, no matter what you try to change, history will self-correct so that the timeline remains consistent. It's like the universe is running an autocorrect feature for reality. Whatever you do in the past will always align with events that have already happened. Let's break it down. Imagine you travel back in time to prevent an invention from being created. According to Novikov, something will always interfere. Maybe you accidentally inspire the very invention you were trying to stop. The loop stays intact, and history unfolds exactly as it was meant to. The past is flexible only in ways that keep it logically consistent. This principle has huge implications. It suggests that time travelers aren't free agents. They can't just alter events on a whim. Instead, they become part of history, playing the role they were always destined to play. And here's the kicker. If time loops exist, they must already be playing out around us without causing contradictions. So could time loops be real? If they are, Novikov's principle suggests that we might never even notice. The universe might be a master of self-correction, ensuring that time remains an unbreakable, logical chain. No paradoxes, no rewrites, just one seamless, unchangeable loop. Chronology protection conjecture. Imagine a world where time travel is not only possible but common. People from the future randomly show up in the past, rewriting history, creating paradoxes, and leaving behind a tangled mess of cause and effect. Sounds chaotic, right? Well, according to Stephen Hawking, nature simply wouldn't allow such a disaster to unfold. His answer? The chronology protection conjecture, a theoretical safeguard built into the fabric of the universe to prevent time loops from ever forming. Hawking proposed this idea in 1992, suggesting that while Einstein's general relativity allows for solutions like closed time-like curves, CTCs, which could theoretically permit time travel, something in the laws of physics steps in to prevent them from becoming reality. Essentially, the universe acts like a self-policing system, making sure no one can break causality or rewrite history. But how does it work? One possibility is that the moment a time loop begins to form, quantum effects kick in and destroy it before it becomes stable. Some theories suggest that vacuum fluctuations, tiny, unpredictable quantum changes in spacetime, would build up to an infinite level near a time loop, ripping it apart before it can be used. Others believe that gravity itself could create an instability that prevents time travel from ever happening. So, if Hawking was right, this means that even if we discover a theoretical way to travel back in time, nature will always find a way to shut it down. No paradoxes, no rewriting history, no alternate realities, just one continuous, untouchable timeline. But here's the real question. What if the chronology protection conjecture isn't an absolute law, but just a tendency? Could there still be hidden loopholes, conditions where time loops might briefly exist before collapsing? If so, the universe might not be as rigid as we think, and the dream of traveling through time might not be entirely impossible. Experimental investigations. Alright, we've talked about theories, Gödel's rotating universe, closed time-like curves, and even Hawking's idea that time travel is off limits. But what about real-world experiments? Has anyone actually tried to prove that time loops could exist? The short answer? Yes. And some of the results are surprisingly intriguing. One of the most well-known names in this field is Dr. Ronald Mallet, a physicist who has spent decades working on a theoretical time machine. His idea? Using ring lasers to create a circulating beam of light strong enough to twist space-time itself. If space can be bent, and time is linked to space, then maybe, just maybe, a powerful enough laser could create a closed time-like curve, making time loops possible. While Mallet's work is still in the theoretical stage, it's one of the few serious attempts to explore time loops in the lab. But lasers aren't the only approach. Some physicists have looked at the quantum world for answers. In 2014, a study simulated photon-based time travel using quantum entanglement. Scientists at the University of Queensland managed to create a system where a photon, a particle of light, appeared to interact with a past version of itself, essentially behaving as if it were inside a time loop. While this wasn't real time travel, it hinted that nature might not completely forbid information from moving in strange loop-like ways. Then there's the research on black holes and wormholes. Some theories suggest that rotating black holes like Kerr black holes could naturally create conditions for time loops to exist. The challenge? We can't exactly step into a black hole and check. However, astronomers are constantly studying the effects of black holes on space-time, looking for signs that time behaves differently near their event horizons. So, what's the verdict? We don't have a working time loop yet, but experimental research is pushing the boundaries of what we know about time. Could future discoveries reveal that time loops are not only possible but already happening around us? Science isn't ruling it out just yet. Time loops in fiction versus reality. We've all seen it in movies. The protagonist wakes up, lives their day, something bizarre happens, and then boom! They're back at the start, trapped in a loop. Whether it's Groundhog Day, Edge of Tomorrow, or Tenet, time loops have become a storytelling goldmine. But here's the big question. How close is Hollywood's version to scientific reality? In fiction, time loops often work as a reset button, forcing characters to relive the same moment until they break the cycle, whether through self-improvement, solving a mystery, or fulfilling some cosmic purpose. But in real physics, time loops, if they exist, wouldn't necessarily follow a narrative arc. Instead of a magical force trapping someone until they learn their lesson, time loops in nature would be an inherent feature of space-time, a direct consequence of Einstein's equations, quantum mechanics, or even higher dimensional physics. So, could someone actually get stuck in a loop like in the movies? If closed time-like curves (CTCs) exist, it's theoretically possible that information or even conscious beings could experience cyclical time, constantly returning to the same point. But here's the catch. Novikov's self-consistency principle suggests that any action taken in a time loop must be consistent with history, meaning you wouldn't have free will to break out of it. And then there's Hawking's chronology protection conjecture, which suggests time loops should be physically impossible, nature's way of keeping history untouchable. That means no respawning, no rewinding, and no magical resets. So, while fiction lets us fantasize about infinite do-overs, reality is a bit more stubborn. Time loops may not follow Hollywood rules, but who knows? The universe still has plenty of secrets left to uncover. Maybe one day, science will reveal that fiction wasn't too far off after all. So, could time loops really exist? Or are they just a wild sci-fi fantasy? While science hasn't confirmed them yet, theories suggest they might be possible under extreme conditions. Maybe the universe is hiding its biggest secrets in the folds of time itself. What do you think? Are time loops real, or just a mathematical illusion? Let me know in the comments. And if you love exploring the mysteries of time and space, don't forget to subscribe to InnoVision Tech. What if I told you that most of the universe is invisible? That out there, beyond the glittering stars and galaxies, lie vast, terrifying regions of darkness. Places where the laws of physics seem to break, where entire galaxies vanish, and where unseen forces pull us toward an unknown fate. Scientists have discovered some of the most bizarre, mind-bending mysteries hidden in the darkest corners of space. From enormous voids to invisible matter and forces we can't explain. What's really lurking in the cosmic shadows? Buckle up, because today we're diving into the deepest, darkest secrets of the universe. The Boots Void. Imagine looking into the night sky and finding absolutely nothing. No stars, no galaxies, just a vast, eerie emptiness. That's exactly what astronomers found in 1981 when they discovered the Boots Void, one of the largest and most baffling empty spaces in the known universe. This void, spanning nearly 330 million light-years, is so massive that if the Milky Way were placed inside, it would still seem like a tiny speck. Now here's the creepy part. This isn't just a dark region of space where there are fewer stars, it's an area where there should be thousands of galaxies. But instead there are only a handful. Scientists call it a supervoid, but even that term doesn't fully explain how something this enormous and empty could exist. Some theories suggest it formed due to smaller voids merging over billions of years, creating a cosmic desert. But others believe something even more mysterious is at play. Could this void be evidence of something beyond our understanding of physics? Some speculative ideas even suggest advanced extraterrestrial civilizations could have engineered such a void by harvesting galaxies for energy. It sounds like science fiction, but the truth is, we have no definitive explanation. Whatever caused it, one thing is clear. The Booties Void is one of the greatest enigmas of the cosmos. A place so vast and silent it challenges everything we know about how galaxies form and the large-scale structure of the universe. If there's anything lurking inside, we may never know. Dark matter. Right now you're surrounded by invisible matter. You can't see it, touch it, or interact with it in any way, but it's there. Scientists call it dark matter, and it makes up about 27% of the universe. Yet no one knows what it really is. Here's the weird part. If you remove all the stars, planets, and galaxies from the universe, more than 80% of its total mass would still be left behind. This hidden mass is what holds everything together. Without dark matter, galaxies would fall apart because they rotate too fast for their visible mass to keep them intact. It's like some invisible glue is keeping the cosmos from unraveling. But if it's so important, why can't we see it? Well, dark matter doesn't emit, reflect, or absorb light, meaning our telescopes are completely blind to it. Scientists have only been able to detect its presence indirectly through gravitational effects on visible matter. It's like watching trees sway without seeing the wind. And here's where things get even stranger. We have no idea what dark matter is made of. Some theories suggest it could be made of yet undiscovered particles, while others propose it might be linked to an entirely new dimension of physics. Some even wonder if we're looking at the problem all wrong and that gravity itself needs to be redefined. The search for dark matter is one of the biggest scientific mysteries of our time, and solving it could unlock secrets about the fate of the universe itself. But until then, we're left wondering, what is this ghostly presence lurking in the shadows of space? Dark energy. For the longest time, scientists believed that gravity would slow down the expansion of the universe, maybe even stop it completely one day. But in 1998, astronomers made a shocking discovery. Instead of slowing down, the universe's expansion is actually speeding up. Something unseen is pushing galaxies apart at an accelerating rate, as if some mysterious force is actively stretching space itself. They call this force dark energy, and it's even stranger than dark matter. In fact, dark energy makes up a whopping 68% of the universe, meaning most of what exists is something we can't see, touch, or explain. Think of it like this. If the universe were a balloon, dark energy is like an invisible force making it expand faster and faster over time. But here's the catch. We have no idea what dark energy actually is. Some theories suggest it's a property of empty space itself, while others propose that it could be some unknown repulsive force woven into the fabric of reality. But what does this mean for the future? If dark energy continues its relentless expansion, galaxies will drift further apart, stars will burn out, and the universe could eventually become a cold, empty void. Scientists call this terrifying scenario the Big Freeze, a future where everything is too far apart to interact, leaving the cosmos in an eternal lifeless darkness. Right now, dark energy remains one of the biggest unsolved mysteries in physics. It's not just an invisible force, it's the key to understanding the fate of the entire universe. The more we learn about it, the more unsettling it becomes. Is dark energy something natural, or are we witnessing the workings of something far beyond our comprehension? The cosmic microwave background. The cosmic microwave background is often called the echo of the Big Bang, a faint radiation spread across the universe that tells the story of how everything began. But buried within this ancient light is something scientists can't fully explain: the cold spot. Unlike the rest of the CMB, which is fairly uniform, this region is noticeably colder and emptier than expected. And we're not talking about a small difference, it's billions of light years across. Some scientists think it might be a supervoid, an area with far fewer galaxies than normal, causing the light traveling through it to lose energy. But here's where things get creepy. The cold spot is so large and so strange that some physicists believe it could be evidence of something beyond our universe. One mind-bending theory suggests it might be the scar left behind by another universe colliding with ours. Yes, a literal bruise from another reality. If true, this would be the first actual evidence of the multiverse. Other ideas suggest it could be a statistical fluke, but the chances of that are incredibly low. Scientists have been scratching their heads over this mystery for years, and despite all our advancements in cosmology, we still don't have a solid answer. Is the cold spot just a weird quirk of the cosmos, or could it be a window into something far bigger than we ever imagined? Dark galaxies. When you picture a galaxy, you probably imagine something like the Milky Way, a swirling collection of billions of stars, glowing clouds of gas, and bright cosmic fireworks. But not all galaxies shine. Some are nearly invisible, composed mostly of dark matter with barely any stars to light them up. Scientists call these eerie, starless entities dark galaxies. One of the most famous examples is Videofy 21, a galaxy located in the Virgo cluster. But here's the bizarre thing. When astronomers looked for its stars, they couldn't find any. The only clue that it even existed was the way it distorted the space around it with its gravity. It's like a cosmic phantom, something we know is there but can't actually see. And dark galaxies aren't just a rare phenomenon. Some studies suggest they could be more common than regular galaxies, meaning much of the universe could be filled with invisible ghost galaxies, drifting in the dark. But why do they exist, and what can they tell us about dark matter? One possibility is that these galaxies formed in regions where star formation never took off, leaving them as dark, empty shells. Another theory suggests that some may have started normally, but had their gas stolen by larger galaxies, effectively shutting them down. If dark galaxies truly outnumber luminous ones, it means our picture of the universe is incomplete. There's an entire hidden world out there lurking in the shadows, just waiting to be discovered. The Great Attractor. Right now, as you're watching this, our entire galaxy is moving at an incredible speed of 1.3 million miles per hour. But here's the question: where are we going? And more importantly, why? Astronomers have discovered that the Milky Way, along with thousands of other galaxies in our region of space, is being pulled toward a mysterious unseen force known as the Great Attractor. It lies about 150 to 250 million light-years away, and it's so powerful that it's dragging entire galaxy clusters toward it. But here's the catch: we can't see it. The Great Attractor is hidden behind the zone of avoidance, an area obscured by our own galaxy's dense stars and dust, making it nearly impossible to observe directly. But even though we can't see what's there, its gravitational influence is undeniable. So what could be causing this massive pull? One idea is that it's a supercluster of galaxies far bigger than anything we've ever seen. Another theory suggests it could be something even more exotic, like a colossal structure of dark matter, bending space on a scale we can barely comprehend. Whatever it is, we're racing toward it at incomprehensible speeds, and we still don't fully understand why. Is the Great Attractor just another massive gravitational anomaly, or are we being drawn toward something far more mysterious lurking in the depths of space? The universe is full of mysteries, and the deeper we look, the more questions we uncover. Are we truly alone, or is something lurking in the cosmic dark? Let me know your thoughts in the comments. If you enjoyed this journey through space, don't forget to like, subscribe, and hit the bell icon for more mind-blowing content from InnoVision Tech. See you in the next one.